This is part 3 of a series of lessons on analytics for bivariate data. In this part, we will consider the case where both the variables are qualitative in nature. So recall that when we have two columns of data for some entities, we have bivariate data. And recall that the two columns of data may be either both quantitative or both qualitative or one quantitative and one qualitative. So in this lesson, we will learn how to perform some analytics with bivariate data when both the variables are qualitative. In part 1, we looked at the case where both were quantitative, and in part 2, we looked at the case where one was quantitative and one was qualitative. So let's look at the example data here. So in this example, we have two qualitative variables, category, so this is category of products ordered, and state for 25 orders. So in this table of data, there's no numbers. And because there are no numbers, we cannot draw any chart, we cannot compute any numeric measures either. We cannot do any analytics with this data the way it is. So to do any analytics with this data, we must first compute some frequencies at least. So when we have two ungrouped qualitative variables, the frequency table is two-dimensional. How many rows and columns are in this two-dimensional frequency table? Well, that depends on the number of unique values in these two qualitative variables. So in our example, there are three unique categories: furniture, technology, and appliances, and there are four unique states: Florida, Georgia, South Carolina, and North Carolina. So we will have either a 4x3 matrix or a 3x4 matrix, depending on which variable we put in rows and which we put in columns. So such a two-dimensional frequency table has a name. It's called a contingency table. So in this lesson, we will learn how to create a contingency table and then what to do once we have the contingency table. So once we have the contingency table, we can do a few things. We can draw clustered column charts or stacked column charts. We can draw clustered bar charts or stacked bar charts. We can perform a chi-square test to check if there is any association between the two variables. If there is an association between the two variables, then we say that the two variables are not independent of each other. A lack of association implies independence. So in this example, an association between state and category would imply that customers in certain states are inclined to order more of one category of items over another category. On the other hand, a lack of association would imply that there is no pattern, that there is randomness, that it's not as if one state favors one category or vice versa. So how does a contingency table look like? It looks like this. In this case, we chose to have states in rows and category in columns, so we got a 4x3 matrix. If we had put states in columns and category in rows, we would have a 3x4 matrix. Both are equally correct. So the numbers in this table denote frequencies. So there were four orders involving Florida and appliances. This gives us total frequency. So of all the orders, 13 orders were from Florida, 7 from Georgia, 2 from North Carolina, and 3 from South Carolina. And this denotes total number of orders for appliances, total number of orders for furniture, and 6 for technology. And here's a breakup of how they were distributed across states. Creating contingency table in Excel, we can create a contingency table in Excel using the COUNTIFS function. We can also create contingency tables using pivot tables. Now both these approaches, either using the COUNTIFS or pivot table, are best demonstrated in Excel. So a demo will be provided in a separate video. Once you have the contingency table like this, what can we do? We can create a clustered column chart of frequencies. So for Florida, we have a cluster of frequencies, one for each category of items. appliances, furniture, technology. So this gives a nice visualization of how the frequencies are distributed amongst states and amongst category of products. We can also do a stacked column chart. So the frequencies are stacked on top of each other. So the advantage here is that in addition to seeing how they are distributed, we can see the total frequency for each state, which was not that obvious in a clustered column chart. And within each column, you can roughly see if the frequencies are roughly equally distributed or unequally distributed. If they are roughly equally distributed, then there's no relationship between the two qualitative variables. If the frequencies are quite unequally distributed, that would imply a relationship between the two variables. We can also do a clustered bar chart. A clustered bar chart is nothing but a clustered column chart rotated by 90 degrees. It has the same amount of information as a clustered column chart. Similarly, we can create a stacked bar chart, and it's almost like a stacked column chart just rotated 90 degrees. Then we can do a chi-square test to see if there's any association. So the chi-square test is performed to tell if the two columns of data are independent of each other or if there's an association between them. So in our example, an association between the two variables would imply that certain states tend to order more of certain category of products. A lack of association implies independence. So to perform a chi-square test, we first have to create a second frequency table from the original contingency table. The second frequency table is for the expected frequencies, assuming that the two columns are independent. So now we have two frequency tables. The contingency table is actual frequencies, and the second table is expected frequencies. Expected, assuming that the two variables are independent. So then we compare these two sets of frequencies to see if they are close to each other or they are far apart. And to do that, we use what is called a chi-square test. So the chi-square test tells us if the two frequencies are close to each other or they are far from each other. If the chi-square test suggests that the two frequencies are close to each other, it implies that the two columns of data are independent, because the expected frequencies were under the assumption that they were independent, and the actual are close to the expected. That means in reality they are independent. On the other hand, if the two sets of frequencies are far apart from each other, that implies that the two columns have some association between them, that they are not independent. Now, chi-square test can be performed in Excel using a function called chi-square.test. So this is the actual frequency table, the original contingency table. From here, we construct a second frequency table called the expected frequency table. How do we construct this table? This 4.68, 5.2, these are the expected frequencies, and they all add up to 25. So how do you get 4.68? So 4.68 is the expected frequency for Florida and appliances. So what we do is we take the total frequency of Florida, 13, multiplied by total frequency of appliances, 9, and divide by the total frequency, 25. So 13 times 9 over 25 gives me 4.68. Similarly, any of these frequencies, how did we get this 0.8? North Carolina and furniture. So North Carolina's total frequency is 2 and furniture total frequency is 10. So for North Carolina and furniture, it's going to be 2 times 10 divided by 25 equal to 0.8. So that's how we construct expected frequencies. And we can easily write a formula in Excel to compute this expected frequency, and then we can copy and paste this formula for the rest of these rows and columns. So when we use Excel's chi-square test function, we provide the actual range and the expected range as inputs, and it gives us a value between 0 and 1. And this value between 0 and 1 is called the p-value. And if this p-value is less than or equal to 0.05, we conclude that the two columns have an association between them. That is, they are not independent. If the p-value is greater than 0.05, we conclude that there is no association between the two variables. So for our example, the chi-square value comes out to be 0.56. Since this value is greater than 0.05, we conclude that there is no association between the two variables, that is, the two variables are independent of each other. And we can see on the clustered chart that the frequencies for Florida are roughly the same for each category. South Carolina, they're exactly the same. Georgia, there's some inequality, but not enough overall inequality to conclude that there's a relationship between state and category. Here I have slightly different data. My category data has been modified a little bit. So if we do a contingency table for this data, it looks a little bit different. And the clustered column chart also looks different. Now here we can see that the frequencies are quite unequal. Here also they're quite unequal. This is 5 and furniture is 0. Here also we have a 0. Here also we have a 0. So it looks like by looking at this clustered chart that there is some association between state and category. So here the contingency table looks different, but the expected frequency table still looks the same because the total frequencies were the same as before. Just the distribution has changed. But now we will find that there is more gap between the actual frequency and the expected frequencies. For example, this is 9, expected was 5.2. This is 3, expected was 4.68. This is 1, expected was 3.12. So when we do a chi-square test, it takes into account these differences and it computes a p-value accordingly. So this new example, the chi-square value comes out to be 0.02, and since this value is less than 0.05, we conclude that there is an association between the two variables. That is, the two variables are not independent of each other. So we can see in this cluster chart that Florida customers like to order more furniture category items, while Georgia customers lean more towards appliances, indicating that states and category are not independent. And that is what is reflected by the chi-square test. So this concludes the lesson on analytics for bivariate data with both qualitative variables.